Hello everyone, this is Physics 30, Lesson 4. We're introducing a proper Physics 30 concept now. This is momentum and impulse. And of course, during class, we will be talking about these concepts in a lot more detail. But just for this video, just so that we can go through the worked example and to keep it simple, we're really just thinking about these equations. We've got our momentum equation, nice and easy. P as a vector is equal to mv. So momentum is equal to mass times velocity. We have this change in momentum concept. This is going to be important as we introduce the idea of impulse. And as a result, we have the impulse momentum equation, which is force multiplied by a change in time. And that could also be mass multiplied by this change in velocity. The units are interchangeable. We have Newton seconds or kilogram meters per second. All of that we will be doing a lot more work on in class. But for today, we're just looking at this example question. It's a 700 kilogram vehicle. It's moving east at 58 kilometers an hour. So hopefully you can start thinking about this as a vector diagram, as a free body diagram, starting to piece the story together. Here's my car. This is east. And it's going a velocity east. Oops. It's going a velocity east. Of course, we've got a bit of a unit conversion to do first of all, because 58 kilometers per hour, we need to turn this into meters per second, because that's our fundamental units. Notice that we've got meters per second in the units for impulse and for momentum, so that's going to be important. And we'll do this, just to be really sure, we'll do this with unit conversions, unit analysis. So I'm going to go kilometers. 1 kilometer is 1,000 meters. That cancels out my kilometers. And then 1 hour is 3,600 seconds. That cancels out my hour. That leaves me with meters per second. And I can get my answer here. 58 kilometers an hour converted is 16.11 meters per second. So there's my velocity, and that's east. Okay, it's now experiencing an impulse of 30,000 Newton seconds west, and we're asked to find what its final velocity is. So it's traveling east, and now it's experiencing an impulse this way. So there's a force. There's a force applied this way that's making up my impulse. And we're going to try and figure out what the final velocity is. So notice that impulse can be equal to two different equations, and that's what we're going to be playing around with. Often you'll see impulse questions giving times, forces. In this case, we have a change in velocity. So we should be thinking about the delta V. We also have a mass, so that's a bit of a giveaway. So let's go ahead and analyze this. We're going to say that the impulse, okay, my vector, I'm always going to put my vector arrow on the top of I just in case I confuse it with current. So my impulse here is mass times delta V. And that's going to give me mass and then Vf minus Vi. Okay. So I can put my values in. I'm also going to note the positives and negatives. I'm going to treat my east to be positive and my west to be negative. So my change in momentum, my impulse, is actually going to be a negative value. And I'm told what that value is there. It's 30,000. So I'm going to say negative 30,000 Newton seconds is equal to 700 kilograms. That's the mass of the car. And then Vf, which is what I'm trying to find out, minus, and now I've got my plus 16.11 meters per second. So minus 16.11 meters per second. And then if I divide my 30,000 divided by the 700, well, it's a negative 30,000, I'm going to get negative 42.857. And that's my meters per second. And that's equal to the VF minus the 16.11 meters per second. And so now I just have to add that 16.11 to my negative 42. And that gives me a negative 26.747 meters per second. And that's my final velocity. My final velocity is going to be 26. I'm just going to check my significant digits. Significant digits here are 3 and 3 and 3. So I'm good to go there. 26.7 meters per second. And I've got a negative sign. So I'm going to say that that is west, or negative west. Okay, so example number 2. A little bit of recap from class on this one. We're dealing with Ft, in other words, force multiplied by a change in time. This is going to give you the impulse, and the other way of saying impulse is that you have a mass multiplied by a change in velocity. So this means we can play around with this idea of increasing force, decreasing time, or decreasing time, increasing force in particular scenarios. We can play around with this formula, but basically to get the average force acting on something while it's changing momentum, you can just play around with this formula, and that's the general idea. So in this example, we're going to be looking at some graphing, and this is looking at the areas underneath a graph for the force, the net force or the average net force applied for a period of time. Okay, and just to remind you, when you're doing these areas under the graph, if it's a positive value, then obviously you're going to take this area under the line. But if it's a negative value, if it's underneath the line, then just bear in mind or remember that the area is going to be up to the horizontal x-axis here. So it's this shaded area here. And of course, when you're doing the area under a line, it's an integral, so it's going to be the area of the shape, and of course the area of the shape is length times width, and then it's just a case of looking at what you have on the axis. So in this case we have, we'll call this the length. This is the length F, the force, multiplied by the width, which is time, and of course force multiplied by time is impulse. And that's why the area underneath a force time graph gives you the impulse. So here's a close-up of our example. We're told if the net force acts on a 31 kilogram object, we're going to determine the magnitude of the change in velocity. So just to remind us of the equations we'll need, we're looking at impulse, which is a change in momentum. So if we have a change in momentum, then we're looking at the mass times a change in velocity. In other words, mass times Vf minus Vi. Okay. Now I can already kind of think ahead here. We're asked to find just this change. What is the change in velocity? That's what we're really asked for. So the other piece of this is the idea that a change in momentum, so let's write this again, a change in momentum is also force times time. So Ft is equal to m delta v. So if we're trying to find this change in velocity, we can say that the change in velocity is going to be equal to Ft divided by the mass. And we're given the mass. Thinking ahead, as I already mentioned and we've known from class, is that the area underneath an FT graph is going to be your impulse, or your FT. So this is the area of the graph divided by mass. Okay. So let's go ahead and analyze the graph. Notice that we have a straight horizontal piece of the graph, and then it breaks and gives us this declining straight line. So we're going to have to break this into a few different sections. Again, just to recap that, of course, the area of a rectangle is going to be length times width. Hopefully that's embedded in your minds. So the area is length times width for a rectangle. But for a triangle, okay, the area is going to be length times width divided by 2. Now, these are on your data sheets, so you don't have to worry about them too much, and you'll obviously get used to using them without too much problems. So let's go ahead and break this up. This area underneath the this graph, of course, encompasses all of this here, and it's all above the x-axis, so this is the area that we need to think about. But what's interesting is that we have several different shapes to think about. So even though I'm going to calculate this whole red area, it's important to remember that we need to break it up into manageable pieces. In other words, we need to break it up into rectangles and triangles. So hopefully you can see that this here is going to be a rectangle. I'm just going to label that rectangle number 1, or area number 1. We'll do a calculation down here. And so area number 1 is a rectangle, and so it's going to be length times width. And it doesn't matter which one I choose. I'm going to pick the length to be my force. So it's 5 units, not forgetting that I need to multiply by 10 to the power 2. So I'm going to put that in. It's going to be 5 times 10 to the 2 newtons. Okay. Multiplied by the width, which is my time, and that's going to go from 0 to 8, so that's pretty straightforward. That's going to be 8 seconds. 8 seconds. Okay, and I don't have to divide by 2. I'm going to get my value here, and I can put that in right away. That's going to be 4,000. 4,000 Newton seconds. That's my impulse. Okay, area number 2. Well, if you take a look here, we've got another rectangle right here. This is area number 2. I'm going to get the area underneath. Again, it's a rectangle, length times width. Okay. Oops. Just get rid of that. Okay, length times width. So this time, I'm looking at this. I'm going to call this the length. And so that obviously goes to 3. So 0 to 3. So that's going to be my value here, 3 times 10 to the 2 newtons. And then I'm going to be looking at the time. Well, it goes from 8 to 20. So hopefully we can see that that's 12. That's 12 seconds. Okay, I can do my calculation. That's going to give me 1,200. Nope, my apologies, wrong one. That's going to give me 3,600 Newton seconds. I think that's right. Okay, and then the last area here is this triangle. Okay, so I've got my third space right here, which is going to be my third area. And this is a triangle, so I'm going to have to go length times width divided by 2. Okay, so let's take a look at the values. Well, this edge here is going from 3 to 5, so that's 2. 2, and not forgetting times 10 to the power 2. And then I'm going to go from 8 seconds to 20 seconds. So there's my 12. Okay, 12 seconds. Now it's a triangle, so this whole value has to be divided by 2. And that's going to give me 1,200 Newton seconds. Okay, now I'm just going to add them together. Area 1 plus 2 plus 3 add these together, I get a total impulse of 8,800 Newton seconds. Now I'm asked to find the change in velocity. So this impulse here, this 8,800 Newton seconds is my impulse, which recall is equal to a mass times a change in velocity. And so that means that my change in velocity is going to be 8,800 Newton seconds divided by the mass, which is 31 kilograms. So that's going to give me my answer. It is 283.87, so 283.87 something, and that's meters per second. So I'm just going to check my significant digits. Oh, well, I've got 2, so I need to make this 2 significant digits. I'm going to have to change this to scientific notation. So I'm going to say it's 2.8 times 10 to the 2 meters per second. That's the change in velocity.